Hello, all. Welcome. And we continue our discussion on our Getting Popular series on Verilog, where we are writing a Verilog code for different digital circuits and the logic. So this time, without wasting our time, I would like to explain you how we can code a SR latch, which is a 1-bit memory cell used in the digital logic. Obviously, our aim or objective is to realize this 1-bit memory into this FPGA chip, which is a part of this FPGA board, and then we can actually use it for some bigger circuits and the system in the digital system design. So let us focus on how we can start writing the code, and we will also simulate that code. Before that, we will compile it, and after simulation, we would verify its functionality. That is nothing but a truth table. So if you are new here, so you are encouraged to refer to our earlier modules on Verilog, and then you can better understand what we are talking here. And you are already a little bit experienced, you can easily pick up what we are saying here. Okay, so here is your schematic diagram of set reset latch, that is SR latch. You got it realized using two NAND gates. It is as shown, they are cross-coupled configuration, two input NAND gates and two NAND gates. For NAND gate 1 here, you have two inputs. First one is an inverted set input. S stands for set and bar indicates its inverted input. And the second input to this NAND gate is the inverted output Q bar that is coming. For the NAND gate 2, one of the input is inverted form of reset input, that is R bar. R stands for reset, and another input is output Q from the first NAND gate. So you see this is like a cross-coupled configuration. So as you can see that here is a truth table for this SR latch, and you see that there are two inputs. So obviously there are four possible combination. It's a binary logic. So 2 raised to the power 2 is equal to 4. And or we can say 2 raised to the power n, where n is the number of bits or number of combinations. Okay, so you see here S and R, you have got 0, 0, 0, 1, 1, 0, and 1, 1. There are four possible input combinations, and the output would be for S and R. You see they are inverted inputs already. Here is a logic symbol. We'll explain that in a moment. So when they are both set to 0, 0, so we know that if any one input of either of the NAND gate is set to 0, output is switching to 1, output is switching to 1, and Q and Q bar both cannot be 1 at the same time, or they cannot also be 0 at the same time. So you see that because of this combination, output is set to 1, and Q bar inverted output is also set to 1, which is a forbidden condition in a latch or in a SR flip-flop, so it's not allowed. However, this circuit is used to set the output to be 1 or output to be 0, and accordingly the inverted output would be the complement of this. So how to do that? S bar is receiving the input 0 right here. Obviously, if any one of the input of the NAND gate 1 here in this case is set to 0, output is switching to 1, and R is 1 here. R bar in fact is 1, and this one coming here, that is switching the output Q bar to be 0. So obviously 1, 0 is a perfect combination. When Q is equal to 1, Q bar is equal to 0. And for this case, we say the output of the flip-flop is set to 1. So the output logic 1 is latched. Okay, or logic 1 is latched in the output or in the flip-flop. Next, if you have 0 coming to the R bar input, again here Q bar will be set to 1, and this 1 is coming here, and S bar here is 1. So obviously Q equal to 0. So in this combination you say, okay, I have set the flip-flop, or rather I would say I have reset the flip-flop, because you resetted the output to be logic 0. This is a positive logic we are talking about. How about both S bar and R bar is equal to 1, 1? So you see that if there is an initial output present here, 1, for example, Q equal to 1, so both inputs here are 1, Q bar is equal to 0, and this goes here as a 0, and output here is equal to 1. So there is going to be no change. Okay, and you can assume the initial random output condition here. Okay, so only important combinations, you see that you want to set the flip-flop, have S bar equal to 0. If you want to reset the flip-flop, have R bar is equal to 0. What if you don't have inverted inputs, rather you have straight input S and R? Then it would be just a reverse condition. When you want to set the flip-flop, S should be equal to 1, and when you want to reset the flip-flop, R should be equal to 1. So that's the positive logic. Here you would say you are using the inverted logic. Here is the symbol S bar, R bar, Q bar. This is the symbol for SR NAND gate latch. Okay, now we have understood a basic principle of how the latch works here. Very good. Now it's time to simulate. For that, we need to write a code in Verilog. Remember, you can use system Verilog, you can use VHDL also. System Verilog is a little bit better than Verilog, because it's a system Verilog. We'll see that later. Now switch to next slide. Here you again can see I have this SR latch, and the arrow points to the code I have written. As you can see, the colors used in the code helps us to understand it better. Again, this is from the previous slide. We've got the truth table, we've got the symbol, and we have already known how the latch is going to work here. Now, let us understand one by one the syntax of how we have written the code. This code contains both the design code and the test bench code. The test bench is going to provide inputs to the circuit, and it is going to show us or monitor the output of the circuit. Okay, that's what. So we have got this written in the same line and in the same file. So start here. So first, like if you are new here and haven't referred to our previous modules on the Verilog, you are encouraged to go back to understand the basics, syntax, and how we have used little small code examples to understand and get the Verilog done, so that you can come back here later and get it right here. So I am saying that the 2 slashes, all these are in the green, are my comments. Then we start the syntax module. Always in Verilog, you will have the module and the end module. And in between the module and the end module, I will have my design code. So what I'm going to write, I'm going to give a name to my module. My name to the module is SR underscore latch, or you can simply say SR latch, or simply say flip flop, or whatever. Then in the parentheses, I see I have Q and Q bar. So capital Q and capital Q bar are my outputs, and S bar and R bar are my inputs. So I've got my inputs and outputs. Remember, this sequence can be altered. I can also write S bar, R bar, and then Q bar, or S bar, Q bar, R bar, whatever way you want to write. It's okay. Then I need to tell the Verilog my ports, input ports and the output ports. Ports are the places where the inputs and outputs are going to be reflected. Okay, so I will declare the ports. Output are q comma q bar, and input s bar comma r bar, same as what I have written here. So this is a basic thing. Now I have to call the Verilog primitives. I'm saying it. I would say I have to instantiate the lower level models. What are my lower level models in this circuit? They are simply a NAND gates. I need two NAND gates in order to implement this circuit. So in Verilog, as we have seen before in our previous model, there are already ready-made Verilog primitives, and those primitives are basic gates, including NAND gate. We can call them ready-madely, and just like we are inserting these two NAND gates into this input output ports. Okay, so what I'll do here, I will instantiate the Verilog primitive, which is NAND gate, and we'll see how the wires are connected in the cross-coupled fashion. So first NAND gate, I will simply, the syntax is as shown, NAND N1, or I will simply say NAND G1 or G2, whatever you want to name it. So, and NAND N1. So here we are talking about, and in the bracket, first will come the output of this gate, Q, and then the input. Inputs are S bar and Q bar coming right here. So S bar and Q bar. So here output, then S bar and Q bar. Remember, when you have the primitives, you cannot first have the inputs and the outputs. Output must be occurring here in the beginning. Unlike this case here. Here you can have the sequence changed. Here output must precede the inputs. Second gate NAND 2, I have this gate, output will be Q bar, which is I have written here in the parentheses, and then inputs are R bar, and second input is Q here, which is coming right here. So that's how I have written Q bar comma R bar Q, and end module statement is already there. Now I have to simulate these circuits. For simulation, I have to write a test bench. So here I have left the gap, and you can see that this is the test bench, which is basically providing stimulus to the circuit, which are the inputs, and it will also monitor the output. So we'll see how to do that. So again, module and end module, same as before, module and end module. Test bench also will say module and end module. I have given name top. I can say test bench also. I can give it my any name what I want. And then I have to actually declare the wires and the registers and some other variables in the test bench. We have also explained this concept of wires, or in other words, we call them nets, register, and the variables. So wires for my test bench would be here and here. They will be connected to these instantiated SR latch, Q and Q bar. So wire is Q and Q bar, but now look, I have used the small letters Q, Q bar, and here in the main module, I have used capital letters. So Q gets connected to capital Q, and this Q bar gets connected to this capital Q bar. So it's basically you are saying that this SR latch is inside the box, and outside the box you are connecting the wires. Okay, both at the input and the output side. So wire Q and Q bar, because those are the nets I want to monitor. And register, why I have used register for set and reset, because these two are the variables, and I am going to have those values change. So register is a kind of memory in Verilog, which is used to store values for these variables. I am calling them as variables. Okay, so set and reset, note again here the small letters, and these are different from S bar and R bar. So set is connected to S bar, reset is connected to R bar. Okay, because this is the test bench. Now, same like in this SR latch main design module, I have instantiated a Verilog primitives, for example, NAND gates. I would now instantiate a SR latch as a module in my test bench. So lower level module for inside the test bench would be this latch circuit. So what I'm doing is I will instantiate the SR latch. Again, these are the green are the comments. I will say, I will call the SR latch. Okay, SR underscore latch. Now look at this name, which is matching to this name because I have named SR latch to be SR latch here. So this should match. Otherwise, how would the test bench recognize which module you are instantiating? Okay. So when you write this, the Verilog will understand you are calling this module, which already has been defined here or declared here. So HR latch, and then I'm calling it my module name M1. I'm giving it M1, same. Okay. So for example, or I would say my circuit, whatever name you want to simply say M1. And in the parentheses, I have outputs and the inputs. Now, Q and Q bar, these are the wires actually, Q and Q bar. And I can actually have set and reset right here, but look, I have inverted inputs here. This small symbol says that the set and reset are inverted inputs that I have to provide as a stimulus. Because why? You see in the schematic we are using not S and R, rather we are using S bar and R bar. In other way, try to put your answer in the comments. Can I do here this inverted as set and inverted reset? Can I write them right here instead of set reset? And simply then here I would have simply keep them as it is what you are seeing here. Okay. So basically I am providing inverted logic to the input side. Okay. Now once you define the wires, registers, then you have to write the initial, that is a behavioral block. So it means we are telling that how this the behavior of this circuit is, which we have explained this simply. So I would use behavior block syntax is initial, and in initial, this is the keyword, and then I write begin and then end. Between begin and end, I have used this syntax, or this is a command, is just a monitor. It is monitoring at the specified simulation time the three variables, the two variables actually, that is set and the reset, which are going to change their values. B stands for binary, that's why the B letter is used, and Q is the output net or the wire. N is that slash n is just like printing the output at the next line, and comma set reset q. So we are basically monitoring these three logic levels at these three ports, set, reset, and q. So inside then I am writing first set equal to 0, reset equal to 0, which is set and reset. Remember now, when I have set equal to 0 and reset equal to 0, the stimulus are going to be inverted before feeding it to the latch. Just like it is shown in the truth table. So when I say set equal to 0 and the reset equal to 0, I will have inverted set and inverted reset. And for that, Q is equal to 1. And accordingly, we have seen the truth table before. Then after, we'll see in the simulation how this reflects. And then after 5 time steps, I am changing the reset and setting it to the 1. So reset input is 1 then here. And after 5 time steps, again, I am setting reset to be 0. And then after 5 time states again, I am changing set to be equal to 1. And then that's the end module. So between begin and end, I have to use this monitor command and then just provide inputs to the stimulates, was input or stimulus. Once that is done, now we can simply try to compile this code and see how the output is reflected. Okay, so what you see here, I have used the online Verilog compiler IDE. The name of the provider, you can simply use the Google and type this keyword, unlike Verilog compiler. There are plenty of unlike compilers available, and that you can use to do that. So on this screen, I have simply copy pasted my code, which I have shown you before on this empty page, and with that is the same code. Now we can see that how this code can be executed. So there is this button, execute button. There is also simply Android artificial intelligence. It says that what should we build today, and explore full coding abilities of what you see here. Then you can also have optimize your code, like what you see here. You can just use this one. You can debug your code, you can explain your code, and many options are available. But right now we are just trying to compile this code as it is shown. Okay, you can see this symbol when you type in the Google online Verilog compiler. You go to this one, and then this is a new project. So what you now can do is simply click execute, and we'll see how the outputs are done. Click here, it is running, and look at that. The code got compiled. Okay, so here is the simulated output. So what you see here, there is like at 0 time step, your set and reset both are equal to 0, and the output is X stands for don't care. So that's the initial step right here. Not an initial step, output can be 0 or 1. Okay, but at time step 5, you have set equal to 0 and reset equal to 1, and then output goes to 0. It means when reset is equal to 1, you are resetting the output to be 0. Then you again change as set equal to 0 remains same at time step 10, but reset gets from 1 to 0 here, and then output remains same as in the previous case. So it's the no change here. How about at time step 15, your S set input switches from state 0 to state 1 here, and the reset input remains same, and that means Q is getting set, flip-flop is getting set to 1, logic 1. With the set input 1, Q is 1. With the reset input 1, Q is 0. So that's the logic you are basically getting here. Then you have like SR latch, and here now you say execute. Syntax error, so it's not possible. So do one thing, just say this set and the reset, and here also keep set and reset, and execute maybe now, and we'll see how it goes. So yes, so you see now what changes you have done. You have taken out the inverted inputs from this, and then here you see that at 0 time step, both inputs set and reset are 0, and Q is equal to 1 now. Q is equal to 1. And at time step 5, when reset is equal to 1, output is just same as in the previous state. And at time step 10, again Q is equal to 1, so there is no change. But when you have the uh, reset set equal to 1 and reset is equal to 0, your output is 0. So output is set equal to 0, and output is resetted when your reset input receives the 0. So what we expect in our output, what we expect in our truth table. Okay, so that is it. So you can clearly see that we have provided this inputs and we've got the outputs. So obviously this is like Q is equal to 1 for S equal to 0 and reset. This is forbidden as we see in the table. Again, set 0, reset 0, Q equal to 1. Then Q bar will also be 1 as per the truth table, forbidden. And here at time step 5, reset is equal to 1 and set is equal to 0. So when set is equal to 0, it means in the schematic, you are actually getting the S bar is equal to 0. And that is setting the flip-flop to be 1. And here at time step 15, when your reset receives logic 0, it means S set equal to 1, then Q is equal to 0. It means you are resetting the flip-flop. So at here, this stage, you are resetting the flip-flop. At this stage, you are setting the flip-flop. So how about I just then again say here, let me copy paste or simply say copy and paste it here, and reset is equal to 1 again. So at time step, after again 5 additional time step, so now this condition is set is equal to 1, reset is equal to 1, and now at time step 20, both set and reset should be equal to 1, and we should, in that case, both set S bar and R bar is equal to 1, we should have no change. We'll see what we see. No change in the sense Q should be remaining 0. So we'll see, simulate, and we are waiting for the output, and that's what had happened. Set is equal to 1, reset is equal to 1, Q is equal to 0. That's good. Here, if you want additionally to do something, what you can do is Q bar, type here, and here you would say Control C, and maybe here you will write Q bar, that is 1% B, and not the /n, just take it out, comma, and now look at this. So here what you have done is you are including the 4 outputs. You are monitoring the 4 outputs again. So set, reset, Q, and then the Q bar. You want to monitor 4 things together. So execute and we'll see. That's it. Good. So first condition, Q and Q bar equal to 1, forbidden. Then second time step 5, you have Q equal to 1, Q bar is equal to 0. It means when you are set is equal to 0, that means in the schematics, S bar is equal to 0. You are setting the flip-flop to logic 1. For the next time step, you have both 0, 0. So it is Q forbidden again. Both outputs are switching to 1. For the time step 15, set is equal to 0 and reset is 0. Now we are resetting the flip-flop. Good. And at time step 20, both 1, 1. So it is no change. So we have verified the truth table successfully. If you want to do some changes and play around, you can do that. For example, try having the inverted inputs here, and then accordingly you can see that how things will change. For example, let me have that sign here. Where is that sign? No, I don't see I am able to have that sign. So what I'll do, I will just I cannot copy paste from here also. So exercise for you is that put the inverted symbols here and click the execute button and see how the truth table will change. So you then will verify for different inputs. Okay, so hope you found this module useful. If you did so, share it with others for a wider reach and stay tuned for more engaging content like this. We will continue our Verilog series on different digital design of different circuits. Till then, wish you very happy learning and stay tuned. Consider joining our membership of our channel. And bye bye.